Hello, welcome back to AE 2220 Dynamics. In this video, we're going to go over curvilinear motion of particles. We're going to talk about position, velocity, and acceleration vectors, and then we'll look at the rectangular components of them. Curvilinear motion is a type of motion where the particle is moving along some curve that is not a straight line. That curve is fixed, often described by some parameter, and the particle is fixed to move along that path for all time, or potentially a portion of time that you're interested in analyzing. And an example of this is the cart rolling on tracks, for example, or a roller coaster, the coaster moving along the tracks of it. That can be modeled as a particle moving along a fixed curve. Okay, we're going to start by looking at position, velocity, and acceleration vectors. So what we've drawn here is first an origin with 3 directions shown here. In this case, we're not going to deal with vector directions or unit vectors at this time. We're just going to consider this in general. So we're going to first start by drawing position vectors. So we have a particle P. The particle is at position P at time t, and then P prime at t plus delta t. So we'll start by drawing our first position vector from the origin to the particle, and we're going to call this position vector R. Again, this underline represents a vector, and then we'll have a second position vector from origin to the second position, and we're going to call this R prime. And then we'll write down the relative vector, or the displacement, the change in position. We'll write this as delta R. In fact, let me write that on the inside here. Delta R. In addition to that, the change in the curve we'll call delta S, and that is not a vector. So delta S here is the curve length from P to P prime. So R here is the position vector of the particle at time t, and then R prime is the position vector at time t plus delta t. And then delta R vector is the displacement vector. And then again, this displacement is the change of position during a particular time interval. It is not a velocity, it is a change in position, not over a particular time interval. Okay, what this tells us is that this displacement has both, since it's a vector, it's going to have both magnitude and direction. Let's just keep that in mind. Okay, we can then go and compute the average velocity, and we're going to write this as VA. This is going to be equal to the change in position, delta R, divided by the change in time, delta T. And this is a vector in the same direction as delta R. Now, this is not the instantaneous velocity. This is the average velocity. And again, same direction as the displacement by definition. If we want to compute the instantaneous velocity, we need to take a limit as delta t goes to 0. And we can find here that the velocity vector, instantaneous, is the limit as delta t goes to 0 of delta R over delta t, and that was a vector, which again we can write as well, we'll come back to this actually in a moment. We'll deal with what that is in a moment. For now, I'd actually like you to take a moment and pause the video and think about, or try to think about what direction this is in. So let's say, what is the direction of the velocity vector v? We said that the average velocity is in the same direction as delta R. Is this true for the instantaneous velocity? Go ahead and pause the video and think about this. Okay, welcome back. Hopefully you've had time to think about what your answer is. You can write your answer down in the white space provided, and we're going to go through now and talk about what the direction of v is. So as delta R and delta t gets shorter, p and p prime are going to get closer and closer together. That means that in the limit as delta t goes to 0, v is going to become tangent to the curve because those 2 points are becoming closer and closer together, infinitesimally close to each other, such that it's going to end up becoming tangent to the curve. So at this point, the velocity vector will be tangent to the curve at that particular point. And as a result of this, just as in rectilinear motion, we'll find that the velocity vector is equal to dr over dt, or we can write this as r dot. And in this case, the velocity vector is not pointing in the same direction as the position vector, but it's actually becoming tangent to the curve. And in fact, delta r will become tangent to that curve as well. What about the acceleration? Is the acceleration going to be in the same position? Take a moment and think about that. Will it be tangent to the curve? Will it be perpendicular to the curve? Where will that acceleration be? And we'll go through in a moment and figure out where that is. Okay, so let's start by considering the average acceleration. The average acceleration is we'll just say a sub a, is equal to delta v, so that change in velocity, divided by the change in time. That's our average acceleration. And the instantaneous acceleration we're going to find by taking the derivative, or taking the limit as delta t goes to 0. So we'll write a is equal to the limit as delta t goes to 0 of delta v divided by, let me rewrite that, delta t, and this will be equal to the derivative dv dt such that the acceleration vector is the derivative of the velocity with respect to time, or equal to the second derivative of the position vector, dt squared, or we can write this as r double dot. All of those are true. We will often use r double dot in this class, and we will also use a for the acceleration. So in general, the acceleration vector is not tangent to the path, and it's not perpendicular to the path. It points off in its own direction. Let's use this pink. It just points off in its own direction, and that may not necessarily point to the center of the curve. It may not point, it may not be, well, all we can say is that it's not tangent to the path. Where it points depends on the motion. And just in case you're having trouble with these derivatives, these are covered in section 1.2. We're now going to go through and talk about the rectangular components of velocity and acceleration. We're going to consider a particle P and describe its motion using rectangular components, or Cartesian coordinates is what we would call this. We're going to start, and this is where we're going to start applying this algorithm. We're going to start by choosing and defining a coordinate system. Well, first step is to choose an origin. That's going to be our first step. Let's go ahead, we'll put our origin, let's say right here. Now generally there might be a particular point on a structure. Generally you want to choose a fixed point for your origin. Your origin should be fixed, otherwise you're going to deal with moving reference frames, which is something we'll cover in the next video. We're going to choose a fixed point somewhere in the system, and if there is no fixed point, you will need to define and pick one and say that that's your fixed point. So we're going to choose a fixed reference frame. We'll say our origin is here, and it is not moving, and it's not accelerating. We're going to use Cartesian coordinates, so that's going to be our I. This here is I. I just kind of draw the I as a backwards J for this unit vector. Here is our j, so ij, and then the third is k. So we're dealing here in 3 dimensions. And let's go ahead and here's our particle. So it is going to be, in the I direction, is going to have a position of x of t. In the k direction, it will have a position of z of t. And in the j direction, it will have a position of y of t. So I realize now that I kind of jumped ahead, but we need to choose perpendicular directions or define them. We chose Cartesian coordinates here. Let me write this out for you. We're going to define perpendicular directions. And as you apply this approach, it will become more and more natural, and then you'll start to kind of skip steps without thinking about this. Is exactly what I just did. I chose perpendicular directions, which I chose to be Cartesian in this case. And then something I didn't do is to determine the direction of positive rotation. Determine the direction of positive rotation. And this will be based on your right-hand rule. So in this case, we're going to have positive rotation counterclockwise about our k direction, or any of the other directions as well. Counterclockwise, positive. Okay, the next thing is to define position vectors. And to do this, we're just going to simply draw our position vector. So we're going to draw it from the origin to our particle, and we'll call this R. And we now need to write this out in our chosen coordinate system. Okay, so R here is going to be R of t, which is a vector. Again, underline means a vector. It's going to be equal to x of t times I plus y of t j plus z of t in the k direction. That's our position vector. Let's draw a better square around that. Okay. There. Okay. The third step that we're going to now apply is once we've determined our position vector, we're now going to go and determine velocity and acceleration vectors. We need our position vector first in order to find the velocity and acceleration. And in order to determine the position vector, we need to have a coordinate system chosen. So this is why you cannot just rush ahead and try and guess what the velocity is. You need to systematically go through and define a coordinate system, use that coordinate system to then define position vectors, and then once you have your position vectors, go in, compute the velocity and acceleration vectors. Okay, so velocity here we said is dr dt. So that's going to end up being that our velocity vector is equal, I'm going to drop the function notation, is equal to x dot in the I direction plus y dot in the j direction plus z dot in the k direction. And that is our velocity vector. For acceleration, we're now going to take a derivative of the velocity, so dv dt, and what we'll get now is that r double dot fact, let's just write, we'll keep using a for now. We'll write this is equal to r double dot. And then a is going to be equal to x double dot in the I direction plus y double dot in the j direction plus z double dot in the k direction. That's our acceleration here. Okay, so rectangular coordinates are quite effective when each acceleration component is independent of other directions. And specifically what we mean here is that the acceleration, let's just say in the x direction or the x component, this is equal to some function of time, perhaps the velocity in that direction and the position in that direction. Same thing with the other two directions. And lastly, in the z direction, f of t, vz, and z. And here you can see that all three of these can depend on time, and that's completely acceptable, but they need to be independent of what's going on in the other direction. This is a particular use case. Other times where it's very useful is if you have you would need mixed coordinate systems. For example, if you have a cart that's moving horizontally with a pendulum that's attached to it that's oscillating and rotating, that's a case where you're forced to use Cartesian because because you have a mixture of two types of motion. We will do that example in class later. Okay, so in this case, for the case listed above, the instantaneous position can easily be found by integrating each component. And so here we're doing exactly what we did prior to this when we dealt with rectilinear motion, except now we would apply it to all three directions instead. We would be integrating in all three directions. And a common example of this is projectile motion. Okay, we're going to do a different example right now though, and I encourage you to pause the video and take a moment to try and solve this on your own. Do it on a separate sheet of paper, or maybe if you're doing working on a digital pair of notes, you could do it there. Try to solve this problem, and then after you've done so, I will go through and solve it in this video. You should pause it and then go through it. I'll go through and solve this, and then you can compare your answer to what I get. Okay. Hopefully you've given the example a try. I'm going to go through and solve this problem, and then that will be the end of this video. In the next video we'll be moving on to motion relative to a translating reference frame. Okay, so we are given a particle that is moving along a curve defined by the following set of equations. X is equal to 2 sine t, y is equal to 3 of cosine t, and z is equal to 5. We are asked to determine the acceleration of the particle. So this is a case where all the motion in the three directions as defined by the curve do not depend on other directions. So everything in x depends only on t, everything in y only depends on t, and z is just a constant in this case. So now we're asked to find find the acceleration. So we need to go through our algorithm. In this case, we're going to start by choosing an origin. We're going to choose, we don't need to necessarily draw this out. We're going to choose an origin and directions such that the position vector is, in this case, we're going to simply say that we want our position vector and our coordinate system to align with the curve such that we're going to use Cartesian here. The I component goes in the x is associated with I, y is associated with j, and z is associated with k. So then our position vector, r of t, is equal to 2 sine t in the I direction plus 3 cosine t in the j direction plus 5 in the k direction. So we've chosen our coordinate system to align with that. Again, we didn't necessarily need to draw a picture here, but we've chosen an origin and we've chosen our direction such that this is true. We can then go and compute the velocity. So the velocity is then r dot of t is equal to, now we're going to compute derivatives here. It's going to be 2 times the cosine of t in the I direction minus 3 times the sine of t in the j direction plus 0 in the k direction. And then from there we're going to compute a derivative again, and the acceleration is, and we're going to write this as r double dot is equal to minus 2 sine of t I minus 3 cosine t in the j direction plus 0 k. And that is the solution to the question asked. This was a relatively simple example, but these can get complicated, and you will have to use things like potentially chain rule, product rule as well, for computing derivatives of quantities. So that's it for this video. In the next video, we'll cover motion with relative to a translating reference frame.